All right, let us continue with our lecture on the electroweak standard model. The last time we started with discussing 3 generations of fermions, of quarks and leptons, and we focused in particular on the CKM matrix, which governs the mixing and the transitions between the different generations. And today we come to a different topic, namely CP violation. CP violation is an important property of the standard model, which is also tested experimentally. And CP is violated by a small extent. However, it is observable in a particular set of processes, and we will look at what processes these are. CP violation is also described by the standard model, and the description has to do with the CKM matrix. Therefore, this fits into the overall topic of 3 generations of quarks and leptons. And we will see today where the connection comes from. Let me first define what CP violation is and how we can see whether the standard model is invariant under CP or not. For this, we work in gauge eigenstates. So at the moment, we do not yet use those mass eigenstates for the quark fields that we introduced the last time. And so let me just give you a property without proof. In quantum field theory, CP transformations, first of all, can be implemented in a certain way by transforming the fields. Basically, you know that in every quantum field there is a creation operator for antiparticles and annihilation operators for particles. Therefore, a CP transformation basically has to do with exchanging those creation and annihilation operators for the particles and the respective antiparticles. Therefore, it is clearly connected to simply replacing a field by its Hermitian adjoint operator, because then you exchange the roles of A and B dagger, let's say. And precisely speaking, you can define CP transformations in the following. And the definition has an ambiguity, because in principle the creation and annihilation operators are not unambiguously defined. You could redefine them by complex phases without changing their physical content, and therefore the following transformations for CP also involve some so as follows up to complex phases. Namely, there would be a CP operator, CP that stands for an operator which acts on the operators like quantum field operators. And then you have here, for example, a fermion field psi, CP to the -1 would be given by I gamma 2 times psi bar transpose. So this corresponds to the CP conjugation of a fermion field. There are these Weil fermions where you can use the Weil notation with alpha and alpha dot spinors. So then you can decompose the 4 spinor psi alpha chi bar alpha dot with the same CP transformation. Looks a little bit nicer than with this I gamma 2, because it simply corresponds to exchanging the role of the 2 parts of the Weil spinors. So this is maybe easier to memorize, and it looks a little bit more beautiful than the transformation of the full Dirac spinor. So for a scalar field phi, like the Higgs field, there is the simplest transformation. Phi simply goes to phi dagger. And for a vector field, it transforms into itself times a parity transformation matrix, which basically means that the space components of the vector field get a minus and the time component gets a plus in this transformation. That simply corresponds to space reflection, and the overall field operator transforms like this. And then, for example, if you have such a combination which typically appears in the Lagrangian transformation matrix, which basically means that the space components of the vector field get a minus and the time component gets a plus in this transformation. That simply corresponds to space reflection, and the overall field operator transforms like this. And then, for example, if you have such a combination which typically appears in the Lagrangian psi bar gamma mu p left psi, and you transform the overall combination, so that would be something that appears in the kinetic terms and in the interactions between quarks, leptons and gauge bosons in the standard model, of course. Then this entire combination transforms as follows, namely it transforms into minus p mu nu times psi bar gamma mu p left psi. And then, given this, you can see how to construct CP invariant Lagrangians. So therefore, in particular, one thing is easy to see. If you look at the typical Lagrangians of a gauge theory like the standard model, then the gauge kinetic and matter kinetic terms, they are completely composed out of either vector fields and their derivatives, or out of such objects coupled to vector fields. And then automatically they are always invariant under CP. So there is no way that those Lagrangians violate CP, so they are always CP invariant, no matter.
طيب يعني حسب ما عرفته أن السي بي تتحدث عن الأبعاد. حسب ما عرفته أن السي بي تتحدث عن الأبعاد، وبالتالي نجد من خلال معادلة الدي ار على الدي تي فإن كلما زاد التفاعل عمقا كلما اختلفت الأبعاد. يعني من خلال هذه المعادلة، في هذه المعادلة نجد أن زيادة الطاقة تعبر بنا من المعادلة الإيجابية إلى من الحد الموجب إلى الحد السالب، وهذا يحصل اختراق للسي بي، يعني هذا ستكون غير متناظر. طيب هذا ما تقول لي المعادلة، تقول لي النظرية. تعالوا نشوف ما هو تأثير ذلك. طبعا رأينا تأثير ذلك قبل في الفيديو السابق، رأينا تأثير ذلك في اختلافات الكتل بين الدبليو والزي، بحيث أن الدبليو بالرغم من التفاعل العميق أن الدبليو جاءت كتلتها قليلة طاقات عالية، وأن الزي كتلتها أعلى قليلا من الدبليو. فتعالوا نشوف ماذا يحدث في هذا الفيديو.
So that is an important statement. You cannot get CP violation from any of those terms in the Lagrangian. Good. Third model. Then the gauge kinetic and matter kinetic terms, they are completely composed out of either vector fields and their derivatives, or out of such objects coupled to vector fields. And then automatically they are always invariant under CP. So there is no way that those Lagrangians violate CP, so they are always CP invariant, no matter how the phases are chosen. So that is an important statement. You cannot get CP violation from any of those terms in the Lagrangian. Good. Now let us investigate how we can get CP violation. So the terms which are not listed here are on the one hand the Higgs potential term that might or might not violate CP, and the Yukawa interaction between the Higgs and the fermions that might or might not violate CP. Let us look at both of them. First, the Higgs potential. Which is mu square phi square minus lambda phi to the fourth. And here you see what happens if you replace phi by phi dagger, even if you, so that is correct up to some phase, but no matter what phase you choose, if you replace phi by phi dagger times any phase, this is automatically invariant. And also that is automatically invariant. Therefore, this Lagrangian also conserves CP. So, and you see here maybe that you can identify some possibilities for extensions of the standard model to violate CP. In extensions of the standard model, the Higgs potential might be different. And how would the term look like that has at least a chance of violating CP? It would have to be a term which does not simply contain phi absolute value square. And in principle, there might be such terms which do not only contain phi absolute value square, but products of different Higgs fields without an absolute value square. I mean, why shouldn't that appear? And so in the two Higgs doublet model, for example, you could write down products of two different Higgs fields without the absolute value, which nevertheless are real and therefore can appear in the potential. And then you have the possibility of violating CP with the Higgs potential, but not in the standard model. So then what remains is the Yukawa term, and that can violate CP. But CP can be violated by the Yukawa term. And so therefore, let us now focus on the Yukawa interactions. And they, of course, contain the three generations of quarks and leptons. And as we will see at the end, in fact, it violates CP only if there are at least three generations of quarks and leptons, which is also quite fascinating discovery. So, from our previous section 2.1.
طبعا هذا يتفق مع ما توصلت إليه، لأنه كلما زاد التفاعل عمقا كلما زاد الفرق بين الكتل في الجنريشنز المتأخرة. فهذا يوصف تماما ما شرحته في المعادلة الدي ار على سي دي تي، بحيث أنه إذا زاد التفاعل عمقا انتقلنا للجزء السالب من المعادلة، والتي تخبرنا بأن الأبعاد ستقلب وأن الكتلة يعني ستزيد الطاقة وتقل الكتلة وما إلى ذلك. إذن generations تخبرنا عن التفاعل العميق وتخبرنا على انه السي بي يحصل لها يعني violations، وهذا يتفق تماما مع كتاب الحلقة 54 وما بعده 55 56، وأيضا يتفق مع فرضيتي ومع هذه المعادلة.
We had obtained a certain form of the Yukawa interaction. L Yukawa can be written in terms of those interaction eigenstates without loss of generality in terms of diagonalized Yukawa couplings, where only the CKM matrix appears as one non-diagonal object in the three generations. And so let me write it like this: minus YE IJ times L left I bar phi ER J for the leptons. So this would be the Yukawa term for the leptons. And here the YE without prime is diagonal in the generations. So only diagonal elements here are non-zero. I will write this down in a second. So YE, D, U, they are diagonal. And without loss of generality, the diagonal entries are non-negative real numbers. Okay, then how does it go on? We have the same thing for the down quarks. And here in the down quarks we have the CKM matrix. So we have the product V times YD as a matrix with indices IJ. And even though the Yukawa matrix is now diagonal, the CKM matrix appears here, and that is not diagonal, at least not in general. And then we have QI bar left times phi times DRJ, and finally minus YU IJ, that is again diagonal, QI bar L phi tilde U R J plus the Hermitian conjugate of the same thing. So that was our Yukawa Lagrangian, and as I said already, so the Yukawa matrices are diagonal. The only thing where the generations are connected is the CKM matrix here, which has potentially non-diagonal entries. Let us look now specifically at one of the terms, because so far I've never really written out what the plus Hermitian conjugate is, but that is now important. So let me write down the full expression for the leptons. So only the YE term is now minus YE IJ LL I bar phi ER J minus YE IJ, and then the complex conjugate of this is simply for the spinos the reverse expression ERJ bar times phi decker times LL I. Okay. That is the Hermitian conjugate, and here, in order to make it really Hermitian, I in general have to add the complex conjugated coupling constant. Then the right term is manifestly the Hermitian conjugate or complex conjugated version of the left. However, we have assumed that the Yukawa coupling for the lepton is real, then that wouldn't make a difference, but in general this would be the fully Hermitian combination of the two terms for the leptons. Now, what is now the impact of CP? Under CP, how does this Lagrangian transform? We have seen how all the fermions transform, namely they basically become Hermitian conjugated. So in principle this term under CP just becomes that term. However, under CP the coupling constants are not affected. They are numbers and they commute with those CP operators. Therefore, only those terms here are behaving non-trivially under CP. And under CP, simply the two operator terms are exchanged and the coupling constants remain what they are. Therefore, under CP, simply L I L phi E R J is exchanged with this other term. And therefore, this Yukawa Lagrangian is invariant if all the couplings are real. So you see it from this example. This example term is CP invariant if and only if the coupling prefactors are real. And the same holds, of course, for all the terms. And we have assumed that the coupling, Yukawa couplings are actually real. So that is true. But for the CKM matrix, we have not yet assumed that it is real. And so therefore, it in the end boils down to the question whether the CKM matrix is real or whether it has complex entries. If the CKM matrix is not real, then we have CP violation. A complex CKM matrix required for CP violation. Okay, so that is the big discovery. All the terms of the standard model Lagrangian are automatically invariant except for the one which involves the CKM matrix. And so now we have to ask whether the CKM matrix is real. And in order to do that, we have to use some additional freedom to change our fields and parameters by complex phases. So we can do, for example, QLI is multiplied with a complex phase e to the I alpha I QLI. Okay. Suppose we do that. So each generation of this doublet is now multiplied with a complex phase. That is not a gauge transformation, it is just a real redefinition of our quantum field operator by a complex phase. Because typically the complex phases of these operators do not matter. But how does the Lagrangian change if we replace our field by a new field which has such a phase? Then, again, all these simple terms like kinetic terms and so on in the Lagrangian, they do not change at all because the phase drops out between Q dagger and Q. Therefore, the only term which changes is the Yukawa term. And here, basically, if Qi is replaced by such a phase, then we can absorb the phase in the parameter. So such a change is equivalent to changing the Yukawa matrices or the CKM matrix by a phase. And we can do the same for all the other fields. So we can do it for the right-handed quarks, let's say e to the I beta I, or let's do the same alpha I QR I. So if we choose here the same phase, then we do not destroy the relationship that the Yukawa couplings in the up quark sector have already been assumed real and positive. So if we would choose here a different phase for those two fields, then we would ruin our already achieved, let's say, a simple Yukawa structure. And then we would generate here a complex Yukawa coupling artificially out of a real Yukawa coupling. That wouldn't be good. So we want to make our Lagrangian simpler and not more complicated. Therefore, let's keep the Yukawa coupling here what it was. It was already optimized in a sense. Therefore, we multiply those two fields with the same phase. Then the phase drops out here and the Yukawa coupling stays positive. But for the down quark fields, D, R, J, we multiply with different phases. Then again, all the kinetic terms do not change under this phase transformation, but what changes is now the CKM matrix. So this change is equivalent to a change of the CKM matrix. So the entire replacement of the fields means that the Lagrangian effectively changes such that the Yukawa couplings for the leptons and the Yukawa couplings for the up quarks remain, but the product of the CKM matrix times the down Yukawa coupling matrix element ij changes with the phase e to the I, then minus alpha I plus beta j times itself. Okay, so you can change this product of matrices by such complex phases. And actually, since the Yukawa matrix here is diagonal, that is simply equivalent to the same change just for the CKM matrix. So CKM matrix Ij goes into e to the I minus alpha I plus beta j e ij. Okay, so by using this, what it means is that we can change the Lagrangian without changing the physics, because such field redefinitions do not change the physics, but we can change the values of the parameters of the Lagrangian in this way. And we can simplify the structure of the parameters of the Lagrangian. So for example, we might use this opportunity to make the CKM matrix real, maybe, by redefining it with such complex phases to make the matrix elements in the CKM matrix real. The question is, can we actually make it real by choosing those phases here in the appropriate way? It looks quite general, but you see that we do not have as many phases available as there are matrix entries. For example, in 3 dimensions, it is a 3 by 3 matrix with 9 entries, but here we have 3 plus 3 phases, which are 6 phases, which can change the 9 entries. And actually, only the differences between the 6 phases appear, so therefore actually there are 5 independent phases by which we can redefine the 9 entries of the CKM matrix. So therefore it's not obvious that we can make everything new. But that is what we can do. So can remove some complex phases from the CKM matrix without changing physics. So let's do that. And now comes into play the discussion of how many generations are there. And that
طبعا محاولة جعل الفيزياء ثابتة هي محاولة خاطئة، لأنه مفترض أن لا تحاول أن تجعل الفيزياء ثابتة، إنما تقرأ الواقع كما هو. الواقع يقول لك أنه عند التفاعلات العميقة يجب أن تقتنع أن الأبعاد تنقلب ويظهر ذلك في الكتل، ويجب أن تقتنع بذلك، لكن لا تحاول أن تجعل الفيزيكس as the same. لا يمكن ذلك. وهذا يعتبر أحد الأسباب، ربما يكون أحد الأسباب التي جعلت الستاندرد موديل لا يرى تطور الكتل ولا يتنبأ بهذه الكتل، وإنما يقرأها قراءة من التفاعلات.
Was the big discovery of Kobayashi Maskawa. For which they received also the Nobel Prize. Namely, they discovered that if we have 3 generations, then the CKM matrix has a complex entry which is physical and which cannot be redefined away by such a possibility. However, if we have 2 generations or 1, then without loss of generality, the CKM matrix is real. In other words, we need at least 3 generations in order to have CP violation in the standard model. Let's prove this. Let's say we have ng generations. Then the CKM matrix V is a general unitary matrix. How many real parameters does a general unitary matrix in n generations have, in n by n matrix? It has n square real entries. Ng square real parameters. Then we can redefine it in this way, and we have at our disposal n alpha and n betas. That means 2n minus 1 differences. So we can remove 2ng minus 1 phases by choosing these alphas and betas appropriately. And then we can ask how many parameters remain. So ng square minus 2n minus 1 is exactly ng minus 1 square parameters. Okay, so let's plug in some examples. So what happens if we would have only one single generation, ng equal 1, one generation only? Then you could go through the entire discussion once again from the beginning, and obviously one would not need a CKM matrix, but nevertheless the entire formalism applies also to one generation, and in that case the CKM matrix would now be a unitary 1 times 1 matrix. Unitary 1 times 1 matrix is just one complex phase. And how many phases can we remove? We have 1 alpha and 1 beta at our disposal, 1 difference, so we can remove 1 phase. We have 1 phase minus 1 phase gives 0. So we have 1 minus 1 equals 0 parameters in V, and therefore in particular no complex phase. And so that shows that for one generation we can assume without loss of generality that the CKM matrix is real, and combining it with everything else we said, it means that in one generation the entire Lagrangian of the standard model has only real parameters, and then we have no CP violation. What happens for 2 generations? For 2 generations, the CKM matrix would be a unitary 2 times 2 matrix, and a unitary 2 by 2 matrix has in general 4 real parameters, namely 1 mixing angle and 3 phases, so 4 parameters. And then we have at our disposal 2 alphas and 2 betas, in other words 3 differences. So we can remove 3 phases from our 4-parameter unitary matrix. And so there remains 1 parameter in the CKM matrix after that redefinition. And that means we can remove all the 3 complex phases out of the unitary 2x2 matrix, and what remains is a real 2x2 matrix. A real 2x2 matrix, unitary, is just an orthogonal matrix. So then V would look like this: cosine theta minus sine theta, sine theta, cosine theta. So it's an orthogonal 2x2 matrix with one mixing angle theta, which has a name. It is the so-called Carpipo angle, which was actually introduced in the standard model when people did not yet know about the third generation. So it's just an orthogonal 2x2 matrix instead of a general unitary 2x2 matrix, because we can remove all the 3 complex phases. And so therefore we have no CP violation. Now finally, the case of nature, 3 generations. Then the 3x3 unitary matrix in general has 9 real parameters. We have 3 alphas and 3 betas. In other words, we have 5 differences that we can use to simplify the CKM matrix, and then there remain 4 parameters. In the CKM matrix after that simplification. And does that mean we can choose V real without loss of generality? No, it does not, because if we could choose it in a real way, then it would be an orthogonal matrix. An orthogonal matrix in 3 dimensions has 3 Euler angles, only 3 parameters, but we have actually 4 parameters, therefore there must be 1 complex parameter remaining inside of the CKM matrix. So, but real unitary, that means orthogonal. By 3 matrix has only 3 parameters, and for this reason there remains 1 complex phase.
طبعا أنا كانت لدي فكرة مثل هذه الأورثوغوناليتي والنون أورثوغوناليتي. كان لدي فكرة مثل هذه عبارة عن خاطرة دونتها في كتابي الحلقة 56 على ما أظن. تعالوا نذهب ونشوفها. في هذا الكتاب أو الورقة العلمية الذي يتحدث عن الأفكار في الكتب الحلقة 54 و 55، يعني لماذا هي عميقة لمعادلة ياغميل والطبيعة. هذه ترجمة العنوان، أنه الأفكار في كتب 54 و 55 هي عميقة لمعادلة ياغميل وللطبيعة. لماذا؟ لأنه أنا فرضت افتراض هنا، هنا الافتراض هو في هذه المعادلة. هذه المعادلة هو أن إذا ضربنا طبعا الاف مي يو يعتبر مشتقة الاي اللي هو السترينج تنسور، تعتبر مشتقة الاي فيكتور أو الاي تنسور الذي يمثل البوتنشال على المجال الكهرومغناطيسي. وبالتالي عندما نفاضل الاف مرة أولى تعطينا المجالات المغناطيسية والكهربائية، عندما نفاضلها المرة الثانية تعطينا معادلات ماكسويل اللينيرتي في معادلات ماكسويل. عندما نفاضلها المرة الثالثة مفترض أن تعطينا زيرو، لأن معادلة ماكسويل لا يمكن مفاضلتها المرة الثالثة، لكن أنا اعتبرت أنها لا تعطينا زيرو. وضربت مثل بهذا أنه إذا عوضنا يعني في الطرف الأيمن بدلالة الاشتقاقات حولناها إلى كميات تحرك. هذه الاشتقاقات في الطرف الأيسر حولناها لكميات تحرك في الطرف الأيمن، فإننا نجد أن الA ميو طبعا الF يساوي A ميو ناقص الF يساوي الA يساوي هذه الF تساوي A ميو دلتا دي ميو A ميو ناقص دي نيو A ميو. إذا حولناها إلى مومنتوم تعطينا هذه الايدنتيتي. هذه الايدنتيتي تخبرنا هنا أن هنالك داخل الغاز بي ميو وبي نيو، ثم ضربناها في بي اي وبي نيو، طبعا عبارة عن كميات تحرك لكن في أبعاد مختلفة. هذه القيمة افترض تعطينا زيرو بسبب الأورثوغوناليتي اللي هو على مساحة مقطع التفاعل. يعني مفترض البي مومنتوم التي تدخل في التفاعل بسبب الأورثوغوناليتي لا تؤثر في هذا التفاعل. فضربت مثال قلت لماذا عند الطاقات العالية لماذا نفترض الأورثوغوناليتي، لماذا لا نرفض الأورثوغوناليتي، أو لماذا يحدث نفترض أنه هنالك نون أورثوغوناليتي في هذا الحد. إذا حصل ذلك فإن هذه المعادلة لن تكون يساوي زيرو، وبالتالي نجد أن المشتقة الثالثة للإف ميو نيو لا تعطينا زيرو، بينما يعطينا شيء ما يتغير بموجب كمية التحرك الأخيرة بي اي، وهذه على الشيء ما الذي يتغير أنا افترضت مباشرة تكون طاقات الكتل الجديدة المتولدة، والاختلاف في هذه الطاقات أو الاختلاف في الكتل الجديدة المتولدة. فهي نفس الفكرة التي ذهب إليها الدكتور أو الذي قالها هذا البروفيسور الآن.
And that is the so-called CKM phase delta CKM. And so that means that if the standard model has 3 generations of quarks, then there is precisely one and only one parameter which corresponds to complex entries in the Yukawa Lagrangian, and that violates CP. And so therefore the striking outcome of this analysis is that we have exactly one parameter which is responsible for the CP violating physics in the standard model. So since we have 3 generations, it means the standard model does predict CP violation. And all CP violating effects are related to one single parameter. Delta CK. And that is first of all a very striking prediction, so there is not a lot of freedom and if you measure many different CP violating effects and observables, then they must all be related in the end to this single parameter. And that is of course a very non-trivial statement, very non-trivial prediction which is tested experimentally, and so far experiments have confirmed this simple prediction. And furthermore, the CKM phase appears inside of the CKM matrix, so therefore it is connected to flavor physics. CP violation in the standard model is intimately connected to flavor physics. flavor transitions. So in particular, if you have a process where in principle the process could be mediated or could exist even if there would be only one generation, then that process cannot feel the CP violation of the standard model. In order to be able for a process to feel CP violation, the process must somehow depend on all three generations simultaneously. Otherwise, you could always forget about the other generations and take a real CKM matrix, and then you wouldn't have a CP violating effect. So, and since it must feel all three generations simultaneously, it must basically feel all CKM matrix elements simultaneously. They must all simultaneously appear in the corresponding Feynman diagrams. Otherwise, you couldn't see the CP violation. And now you probably know that the CKM entries, the off-diagonal ones, they are very small. So if all of them simultaneously must appear in a Feynman diagram, then you get a strong suppression, a strong numerical suppression, and the CP violating effect will be numerically suppressed. Okay, so this is an important result about CP violation in the standard model. Let me give you an example of a CP violating effect without calculation. Nowadays, CP violation has been measured in a large variety of observables. And let me give you an example which is particularly easy to understand. Some other examples which are measured and which are important are a little bit more complicated. But here is a simple one. There exists the kaon, which is a meson, a bound state of quarks involving the strange quark. And so there is a k long, which is the long-lived kaon, and that is equal to its own antiparticle. And there is a decay mode, k long can decay into pi plus, E minus, and an anti-neutrino via the weak interactions. And this decay has a certain probability and a corresponding decay rate, gamma L. Or let's call it gamma minus, because we see in the final state a negatively charged electron. And so since this is equal to its own antiparticle, it can also decay into the corresponding final state with antiparticles instead of particles. So there is also the decay k long going into pi minus, E plus, and neutrino. And that would have the rate gamma plus. And now the CP violation tells us that the two processes are not equally likely. They are connected by CP transformations, because if you do the CP transformation of one final state, you get the other final state. And if you would have CP invariance, the two decay modes would have to be equally likely, but they are not. So the experiment tells us that the following ratio, difference of the decay rates divided by the sum. So the relative difference, in other words, is 0.003, 3 per mil difference. And that is a direct observation of CP violations. And this direct observation exactly agrees with the prediction of the standard model involving the CKM phase. So in fact, there are many such observables, and they all agree with the standard model prediction based on this delta CKM. Okay, so that is a great success of the standard model, and in a way it's one additional miracle that we have exactly the number of generations in our quarks which are needed to get CP violations. We do not have more than the bare minimum that is necessary, but we have exactly the minimum number of generations which can give CP violations, and we do have CP violation, and the prediction agrees exactly with data. Having said all that, let me give you a remark, which is a side topic. Namely, there could be a second source of CP violation in the standard model, which you cannot see in Feynman diagrams, but which is a non-perturbative effect. The so-called QCD theta term. So one could add a term to the Lagrangian L theta QCD, which looks like the following: some coefficient A times, or let's say A times epsilon tensor epsilon mu nu rho sigma times F mu nu F rho sigma for the QCD field strength tensor. This term is also gauge invariant. It's basically equivalent to the product of the field strength times its dual field strength tensor. That is gauge invariant and also Lorentz invariant, but it violates CP because under CP basically the indices all behave in the obvious way, but there are three spatial indices and one time-like index, and therefore since the spatial indices change their sign under CP, just the entire term changes its sign. Therefore it is not CP invariant. But it is a total derivative. Therefore in perturbation theory it cannot appear, because there we drop total derivatives, and in Feynman rules it would correspond to a sum of incoming momenta which is zero because of momentum conservation. Therefore, so it cannot appear in Feynman diagrams. And therefore we have never written it down to begin with, even though we could have. But if you go through the non-perturbative treatment of this term without using Feynman diagrams, then you discover that actually it can lead to CP violating effects, and those CP violating effects would have nothing to do with flavor and nothing to do with regenerations. And those CP violating effects which would come from this term are not observed. Therefore, experimentally we have found that the coefficient of this term is zero, or if it's non-zero, it must be extremely small because we do not see its effects. So let's simply say the corresponding CP violating effects are not observed. So it means the coefficient must be 0 or very small, and the experimental limits are around 10 to the minus 9. And so that is actually one of the open questions of particle physics, is the so-called theta QCD problem. Because people try to find a reason why that term should be 0 or why it should be extremely small, such that we do not observe its effects, even though in principle it could be there. But anyway, from the phenomenological point of view, it is correct to drop the term because we have not seen its effects. But so just that you know that in principle such a term would exist.
طبعا هذا السؤال يمكن أن يكون من خلال معادلتي السابقة فيها نوع من الإجابة، لكن يجب أن نشوف ظروف التفاعلات والمواد المتكونة وما إلى ذلك. لكن إجابتي مبدئية أنه عند التفاعلات العميقة فإن الكتلة تنقص، بالتالي يعني هذا الحد بهذا النقصان ربما يصل إلى 10 صناعة 9. هناك مشكلة في QCD والإي دبليو. هناك في الستاندرد موديل أنا لم أتبين حتى الآن خط فاصل بين QCD والإي دبليو. يعني مثلا أنا أعلم أن QCD مع بين كواركات، الإي دبليو كواركات أيضا، يعني النشاط الإشعاعي عبارة عن كواركات. الفليفرز عندما تغلب الفليفرز عبارة عن كواركات. طيب QCD تتحدث عن قوة نووية قوية. قوة نووية قوية هي 10 ناقص 16 متر. الكواركات 10 ناقص 18 متر. فأنت لا يمكن تكون حدود QCD إلى هذه الحدود، لا، يجب إلى QCD أن تكون عندها حد معين ثم يأتي الEW عند حد معين. لكن إذا حاولت أن تجعل QCD إلى آخر الحد والEW آخر حد، يعني 10 ناقص 18، فإنهما تعتبران قوة واحدة. فالEW وQCD تعتبر قوة واحدة. نعم QCD قوية، EW ضعيفة، هذا واضح من ما شرحته في الفيديو السابق وما بينته هنا في الفيديو، أن عند الأبعاد الصغيرة الكتل تضعف. الأبعاد الصغيرة جدا داخل البروتون الكتل تضعف. عند التفاعلات القوية جدا فإن الكتلة تضعف، لأنه الدبليو بوزون أقل كتلة من الزي بوزون. إذا أنت عندما تتحدث عن الإي دبليو تتحدث عن كتل ضعيفة وطاقة عالية. عندما تتحدث عن QCD طاقة قليلة وترابط قوي. بالرغم أن الEW فيه ترابط قوي، لأن الخواص المغناطيسية أيضا تزيد مع زيادة الطاقة. لكن في النهاية هناك تفلتات تحصل في الEW اللي هو في النشاط الإشعاعي، ناتجة من ماذا؟ ناتجة من آلية الفضاء صناعة بعد الدفاع النفسي. إذا ما يفرق QCD بين الEW من الEW أن عند أبعاد الEW يتدخل الفضاء صناعة بعد الدفاع النفسي، عند QCD لا يتدخل. إذا نحن نتحدث الآن عن أبعاد، نتحدث عن أبعاد، فالأبعاد يجب أن تفرق بين QCD والEW. فهذا لا أراه حتى الآن، لم أرى. QCD تتحدث عن كواركات، الEW تتحدث عن كواركات. QCD تتحدث عن تفاعلات بين الكواركات والجلونات، الEW تتحدث عن تفاعلات بين الكواركات فإذا نحن نحتاج لحدود واضحة بين QCD وEW، وإلا ستكون قوة واحدة. هذه القوة الواحدة تعتمد على بارامترات مثل الطاقة والكتلة. عند الأبعاد الصغيرة الطاقة عالية، كتلة ضعيفة. عند الأبعاد الكبيرة كتلة عالية وطاقة ضعيفة، وهكذا. فهذه المسألة إجابتها كالآتي، هو نفس الإجابة التي قلتها، أنها عند أنت تقول QCD وتقول أنها هذا الفيوليشن يعني هذا الفيوليشن هذا الحد هو صغير. طبعا لازم يكون صغير. عندما تتحدث عن أبعاد صغيرة فإن الطاقة تكون عالية والكتلة تكون صغيرة، فلازم يكون هذا الحد يكون صغيرا إذا حسبته عن طريق الكتلة.
Any questions so far? That would basically constitute our summary of CP violation, and then I would show you a little bit of example processes, and then we wrap up our three-level discussion of the standard model, such that next time we would start with higher order discussions of the standard model. Yep. Yeah, for example, it gives an unambiguous definition of matter versus antimatter that you can communicate to everywhere, like we can do with parity violation. And so you can communicate by using parity violation to somebody that you see only on the telephone what you mean by right-handed versus left-handed. Here you can also communicate electrons versus positrons in that way. Yes, right, exactly. And also you see that in such a way from the CP violation that is connected in an interesting way to the baryon asymmetry in the universe, because we ask ourselves, where does the baryon-antibaryon asymmetry come from? There is more matter than antimatter in the universe. In particular, there are more baryons than antibaryons in the universe. And so maybe that has some dynamical explanation. Maybe it's an accident, but maybe it has some dynamical explanation. And this could be such an explanation that in the early universe there were particles, maybe neutral particles, which decay more often into matter than antimatter, and then such an asymmetry could have been created. That is one of the possibilities. I mean, kaons cannot be responsible. If you look at the details, that is known. So it is known that the CP violation that exists in the standard model is not enough to generate the observed baryon-antibaryon asymmetry, but similar mechanisms, if they are present, for example, in the very, very early universe after inflation, coming from grand unified theories, for example, could hypothetically explain the baryon-antibaryon asymmetry. Anyway, it is clear that for this asymmetry to be created dynamically, you need CP violation, and you need a preference of matter versus antimatter in such a way. So this sort of thing would in fact be the simplest way, also the simplest for conceptual understanding how the baryon asymmetry could be created, because you see it directly. In the early universe you might have only neutral particles which are heavy, then they decay dominantly into matter, that's it. But we don't know what is the correct explanation of this. Are there other questions? Okay, then let me give you one or two examples. Some sample processes. And let me begin with the classic flavor changing neutral current process. So for kaons. So for example, anti-strange and down quark together, they form a bound state K0. The notation is historical, and K0 was attributed to be a particle with so-called strangeness number 1, and strangeness number 1 corresponds to an anti-strange quark inside of the meson, so they got it the sign wrong somehow. but that is just a convention. So anyway, this has strangeness number 1 and it contains an S bar. And you can write down the following Feynman diagram, which is a one-loop box diagram, and in the final state you have an anti-down and a strange. And so you see that here you have, for example, W bosons, and here you have up quark, charm quark, or top quark, and here also up quark, charm quark, or top quark. And then the charges are conserved at each vertex, but you convert a down quark into a strange quark and an anti-strange into an anti-down quark in this way. And so basically you change the strangeness number by 2 units, and so this final state would be called K0 bar, and you have delta strangeness by minus 2 in this way. And this process generates a mixing K0 bar mixing, which means that those two mesons are actually not mass eigenstates, but some linear combination between them is a mass eigenstate, and this effect can be observed. Or if you prepare a strangeness eigenstate like K0, then this mixing means that there is an oscillation like neutrino oscillations where the state oscillates between pure K0 and pure K0 bar with a certain oscillation frequency. So that is one such flavor violating effect. Let us sketch the quantitative prediction of the standard model. So this Feynman diagram contains the following important quantities without going into details of the calculations, but what are the key properties of the diagram? At each vertex there is a CKM matrix element appearing, because we have now W boson vertices with quarks, and they depend precisely on the CKM elements. And so at each vertex there is either a CKM matrix element for a strange quark and the corresponding uptype quark. Let's say, let's call this here I, and let's call that here J. Then, for example, at this vertex we get a CKM matrix element V I D. Then at this vertex we get V star I S, and at the other we get similar things, V J D times V J S complex conjugated. So we get a product of 4 different CKM matrix elements. Then what else do we get? Then we get a Feynman loop diagram, and in this closed loop we get an integral over the momentum which flows through the loop, and there will be some complicated integral, but at the end the integral will have some result. And what will the result depend on? The result will in particular depend on the masses which appear in the loop. Which masses appear in the loop? So let's simply say loop function which depends on the masses, and it depends on the masses mi divided by mw and mj divided by mw. So it will depend on some mass ratio of these particles. Now, without doing the calculation, how would such a loop function typically look like? We can do a Taylor expansion in the small mass ratios, because the W mass is much bigger than the masses of the quarks, except for the top quark, but since the top quark is so heavy, its contribution anyway is strongly suppressed. Therefore, the interesting cases are the light quarks, and then the mass ratio here is very small. And then we can approximate the loop function by a constant plus higher order terms in those small mass ratios. So typically, if you have some experience, you know that it will depend quadratically on the masses mi squared divided by mw squared plus mj squared divided by mw squared plus higher orders. And the constant term, which is not suppressed by the mass ratios, cannot depend on the indices, because otherwise it would be suppressed. Okay, now from this simple sketch of the contributions we can already draw a very important conclusion, which is true in this process, but actually true in many processes like it. Namely, in the standard model, such flavor-changing neutral current processes are threefold suppressed. So there is not just one suppression, but there are three different suppression mechanisms at play simultaneously. And that means that all such processes are extremely small and have very small probabilities in the standard model. So what are those three suppressions? The first suppression is, of course, that it's a loop process which appears at higher orders in Feynman diagrams. Why not at tree level? Because there is no tree-level flavor-changing neutral current in the standard model. That is what we proved. There are no flavor-changing neutral current interactions because they drop out. So we need loops in order to have flavor-changing neutral currents, but loops are always suppressed by a loop factor 1 over 16 pi square, which is a percent. Okay. So automatically we get a percent level prefactor, which suppresses this role. Flavor-changing neutral currents only appear at higher orders in Feynman diagrams. Then the next suppression is the CKM matrix. Of course, in order to generate flavor-changing neutral currents, you have here some CKM matrix element. For example, D goes to U and U goes to S. D goes to U is big, so that is first generation, but then you would have first generation, second generation, so an off-diagonal entry which is small. Or you could have D going to C, then you have first to second is small, C to S is large. But you always have at least one small factor from an off-diagonal CKM matrix element. So the off-diagonal elements are small. And that is actually simply an experimental observation. They wouldn't have to be small. It could be a matrix with very large off-diagonal entries from the theory point of view, but it isn't. It's just an experimental fact that the off-diagonal elements are small. But once we know about this, then we see that the flavor-changing neutral currents are suppressed by here at least 2 powers of these small off-diagonal entries, which comes on top of the loop suppression. And that is not even the end. There is a third suppression, which is the so-called GIM mechanism. Which comes from the behavior of the loop. If you look at the loop function, then you see here the following. The loop is multiplied with this product of 4 CKM matrices, and then of course you get a sum over the index ij. What happens in this sum? In the sum you get here, for example, one term b I d times v star I s. What happens if you sum over I? What is this combination? This is of course a matrix multiplication. So sum over I. It's a matrix multiplication of V times V dagger. But V is a unitary matrix. Therefore, if you do V times V dagger, it becomes the unit matrix. So if you extract the ds entry of the unit matrix, it gives 0. So the sum over I of this is 0. It's 0. What does that mean? So that is the unitarity of the CKM matrix. Where does this sum appear? Here the sum appears, but times the loop function, but the loop function contains a constant term which doesn't depend on the masses. Therefore, the constant doesn't depend on the indices. So if you do this, then the constant term out of the loop function drops out. And then the only thing that remains are the higher order terms, and the higher order terms involve extremely small mass ratios of small quark masses divided by the heavy W mass. And then you have the third suppression. So therefore the constant term drops out. Only mi or j square divided by nw square terms remain. These are the three suppressions, and they are all independent of each other, and they all come on top of each other, and therefore such processes are extremely small and very much suppressed. And actually all of this was known very early on, in particular by Jim in the 1970s, and they used that to predict the mass of the charm quark. Because even before knowing about the charm quark, you can do this calculation. And you see then in the end, from this analysis, the dominant term will be the one with the highest quark mass which plays a role. And the highest quark mass which plays a role will appear as a quark mass square directly in the final prediction. Therefore, in the end, the final prediction will be very strongly depending on the highest quark mass of relevance of the process, and therefore they can use this experimental result to predict that highest quark mass of relevance, which was the charm quark mass. And that prediction turned out to be correct. So these are the three suppressions of flavor changing neutral currents. Let me just give you a small example how else it could be. For example, beyond the standard model, there is the 2 Higgs doublet model, where you could have, for example, this Feynman diagram, strange quark, down quark, then a new Higgs boson, D, R, and S. And then if you have this new Higgs boson coming from the 2 Higgs doublet model, this has or can have 3-level flavor changing neutral currents. And then there might be simply those Feynman rules where the Higgs couples to down and strange quark immediately. And then there is no loop suppression. There is no CKM suppression, because that is a different matrix which might have very large off-diagonal entries. And of course there is no Jim mechanism. So all three suppressions are absent. So, but again, of course, experiment agrees with the standard model, which has all those suppressions. What does this tell us about physics beyond the standard model? It tells us that such ideas are probably wrong. You cannot have new physics with such Higgs boson couplings, because that would probably ruin the agreement with experiment, because it might give rise to a million times higher rates for such flavor changing neutral currents, unless you make those couplings extremely small, and that is what you have to do if you consider such extensions of the standard model. So again, this is something to keep in mind once you go beyond the standard model. Then let me also talk about CP violation a little bit. So surely this Feynman diagram would also correspond to the CP violation of kaons. So this would generate the k-long mass eigenstate, which has then the CP violating decay. And you can see this is a Feynman diagram where actually all three generations simultaneously appear. because you have down and strange in the external lines, and first and second generation, and in the loop there can appear the top quark. And so this is a diagram which can fill all three generations simultaneously, and therefore from such Feynman diagrams you can get CP violating effects. And that is in line with what we said before. But let me now give you some other example, which is also interesting and important to know for current particle physics, namely electric dipole moments. Electric dipole moments. Electric dipole moments are quantities which are directly CP violating. So let's say you have here the electric dipole moment of a fundamental particle. An electric dipole moment basically is a vector in 3 space. It has a direction and magnitude. And if you have a fundamental particle which might have an electric dipole moment, then the orientation of the dipole moment must be connected to the fundamental properties of the particles, but the particle has only one direction which is singled out, and that is the spin. Therefore, if the fundamental particle has an electric dipole moment, this must be proportional to the spin of the particle. However, if you do a time reversal, then under a time reversal the spin becomes, it's negative, because spin basically corresponds to a rotation. And therefore, as a consequence, under time reversal, the electric dipole moment would also have to change its sign. However, you measure an electric dipole moment by applying a homogeneous electric field, and under time reversal, homogeneous electric fields do not change their sign. Therefore, the interaction energy between the particle and the electric field changes its sign under time reversal. And that means the Hamiltonian for that particle is not invariant under time reversal. If the EDM is non-zero. And from quantum field theory, without proof, we know that there is always CPT invariance. Hence, P violation is equivalent to CP violation. So therefore, electric dipole moments of fundamental particles like electron, proton, neutron, and so on are a sign of CP violation. Good. And these electric dipole moments are particularly interesting because they are observables which are directly a measure of CP violation, but they have nothing to do with flavor. So these are completely flavor independent observables for CP violation. And that makes them very interesting, and there are many experiments searching for such electric dipole moments. And so, for example, one searches for EDMs of the electron, of the neutron. The neutron is particularly good because it has no electric charge, but in principle one could also search for the proton and also for the muon and so on. And so far one has not seen experimentally such an electric dipole moment. But in principle, the standard model predicts that such electric dipole moments must be non-zero, because obviously in the standard model we do have CP violation. But let us understand how big is the prediction of the standard model for these EDMs. And from what I said before, you should now understand, in the standard model we need 3 generations in order to create CP violation, but these are flavor-independent observables. Therefore, you need Feynman diagrams to create electric dipole moments where all 3 generations appear simultaneously, and those will be very complicated Feynman diagrams. So let me give you an example. For example, for the down quark, I had here the following Feynman diagram. In the end, you need an interaction between the down quark and the photon, which corresponds to an electric dipole moment interaction. And this can be done in the following way. Here the down quark comes in. Then you have a loop with a W boson and a charm quark, for example. Here the photon couples to this charm quark. Then it goes on. The charm quark could become, for example, a bottom quark. Then you have here another W boson. Here you could have the top quark. And here again you have the down quark. And in order to make it a one-particle irreducible diagram, you could have here, for example, a gluon exchange between the charm quark and the top quark. And then you have a Feynman diagram with 1, 2, 3 loops. And you have first generation, second generation, third generation of quarks simultaneously appearing. And it involves 2 powers of the strong gauge coupling and 4 powers of the weak gauge coupling. And it involves, of course, lots of off-diagonal CKM matrix elements. Basically all off-diagonal CKM elements are simultaneously appearing. Therefore, this diagram is super suppressed. But from this Feynman diagram, one would get a prediction for a non-vanishing neutron or proton electric dipole moment. Similarly, for the electron, you can do similar Feynman diagrams, but for the electron, you need that maybe a 4-loop diagram, because first of all, from the electron, you need some couplings in order to make quarks appear. And then all 3 generations of quarks have to appear. So, and you need external electrons. So basically, you can attach something here with external electrons, and then you get a loop diagram for the electron EDM. So electron EDM at the 4-loop level. But again, for example, in the 2 Higgs doublet model, you might have simply such a Feynman diagram. Okay, maybe supersymmetry. You could have this electron here, the superpartner of the electron, this electron, and here some neutralino fermions, superpartners of all the standard model fermions, and here a photon. Then you have at the 1-loop level such a Feynman diagram which can give rise to CP violation. And therefore, again, extensions of the standard model can give predictions for electric dipole moments which are many, many orders of magnitude higher than the predictions of the standard model itself. And then you need to watch out that you do not break the agreement between standard model and experiment in this way. On the other hand, this thing that you see that in principle other models easily predict much larger electric dipole moments, combined with the fact that we need to explain the baryon-antibaryon asymmetry of the universe, where the standard model CP violation is not enough, motivates searches for electric dipole moments. maybe one will find one such non-vanishing EDM, which then inevitably would prove the existence of physics beyond the standard model in connection with CP violation, and that would be a very important information in understanding, for example, cosmology. Therefore, those experiments are done and they are very interesting to observe. All right, let me finish the lecture by simply summarizing the main properties of the standard model. And either today or in the beginning of the next lecture, I will give a very brief summary of the Feynman rules, as I promised, and then we go on with higher orders. But let me first show you a summary of the miracles of the standard model. So without much comment, so there was first automatic baryon and lepton number conservation. And remember, that followed simply from the field content of the theory. Field content plus gauge invariance plus renormalizability. We obtained accidental baryon and lepton number conservation. Then the second is that we automatically break spontaneously SU2 left cross U1 hypercharge to U1 for the electric charge. And here it is automatic that after the Higgs acquires a vacuum expectation value, there will necessarily be an unbroken U1 gauge group, and this unbroken U1 gauge group necessarily is a linear combination of hypercharge with one of the SU2 generators, and without loss of generality, we can take it as hypercharge plus P3. And this is just our choice, but it is automatic that there must be such a linear combination which remains unbroken. And that followed from one single Higgs doublet with hypercharge equal to 1/2.
طبعا ناقشنا هذا الأمر، وأنه قلنا أنه التفاعلات العميقة تكسر هذا النوع من السيمتري، وتصبح بدل ما SU2 كروس SU2 تعطينا U1 ربما تعطينا U2 SU2 أيضا، وهذا يعطينا جسيمات عالية الطاقة وجسيمات يعني لا تعتمد على الزي بوزون، أو حتى أن الزي بوزون يعني يتغير أيضا، وبالتالي تعطينا جسيمات مختلفة الكتل، والSU2 دائما تعطينا جسيمات مختلفة الكتل، والفرق بين كتلها تكون عالية هكذا يعني عند التفاعلات العميقة. وقد ذكرت لكم الفيديو الخاص بالبروفيسور كلوديا عندما تحدثت عن أنه اليونيتريتي مكسور في التفاعلات عالية الطاقة، بحيث أنه تظهر كمية ضخمة من الجسيمات لا تتنبأ بها الستاندرد موديل.
Then the third miracle was the three-level row 3 equal to 1, or equivalently MW to MZ is equal to cosine theta, which is the same as GW divided by the square root at tree level, of course, and that followed from custodial symmetry. The symmetry the standard model has on top of gauge invariance, namely an approximate SU2 left cross SU2 right, which is spontaneously broken to an SU2 custodial in the vacuum. Then, regarding three generations, there is no three-level flavor changing neutral current. For example, in the Z and Higgs interactions, whereas in extensions of the standard model, Z boson or Higgs interactions could easily have such flavor. Regarding three generations, there is no three-level flavor changing neutral current. For example, in the Z and Higgs interactions, whereas in extensions of the standard model, Z boson or Higgs interactions could easily have such flavor changing neutral currents. And that, of course, has this impact here on flavor changing processes. So we have three suppressions of flavor changing neutral current processes. Then we have just one single source of CP violation. Delta CKM, and that corresponds to exactly three generations. And this statement here ignores the theta parameter from QCD, which would be a second source of CP violation. But even including that, one would have precisely two parameters for all CP violating observables. And then maybe I would like to add here a statement on neutrino masses. We didn't put in right-handed neutrinos into the standard model field content, and then automatically the neutrinos are massless. So we have no neutrino masses. And since we didn't put in the right-handed neutrinos, that is an automatic consequence, so it's maybe not a miracle in the same sense. But what is interesting in this connection is that then at the dimension 5 operator level, there would be this single dimension 5 operator which would generate Majorana neutrino masses. And so that could naturally explain why the neutrino masses are as small as they are. So it would provide a rationale for this observation. All right, so this is the...
طبعا أنا ذكرت أن مع زيادة الطاقة فإن طاقة التفاعل فإن الكتل تنقص والطاقة تزيد، طاقة الجسيمات الخارجة من التفاعل. هذا الأمر ينطبق على ماذا؟ ينطبق إلى حدود معينة من مركز التفاعل أو المكان الذي حصل فيه التصادم إلى نهاية مساحة مقطع التفاعل. بعد ذلك يصطدم الجسيم بفضاء رباعي الأبعاد كامل الدسم، سرعة الضوء فيه على سرعة. هنا إذا كانت الطاقة عالية جدا فإن الجسيم يتحلل، وهذا ما يجعل الدبليو تتحلل مباشرة إلى لا تظهر للعيان وتتحلل مباشرة. أيضا الزي نفس الأمر، طاقتها عالية، طاقتها أقل قليلا وكتلتها عالية. أيضا الكتلة عندما تصطدم تخرج من وسط التفاعل وتصطدم بالفضاء رباعي الأبعاد فإن أيضا تتحلل، لأنه أيضا الفضاء ثنائي الأبعاد أيضا يتحكم في فضاء رباعي الأبعاد خصوصا على سطح الأرض، وبالتالي يجد كتلة هذه كتلة عالية أيضا طاقتها عالية لكن ليست بقدر الدبليو، وبالتالي يحلل هذا الزي إلى جسيمات متشابهة. طيب، فنجد أن الدبليو كتلته تنقص وطاقته تزيد، وبالتالي لديه سرعة عالية جدا. طيب، إذن وسط التفاعل كتلة تنقص طاقة عالية. هذا يعني أنه كلما دخلنا التفاعل عميقا كلما الكتلة ناقصت والطاقة زادت. طيب، إذا الكتلة حافظت على هذا المستوى أنها تكون قليلة والطاقة أيضا قليلة، فإن هذا يولد جسيم يسيطر عليه الفضاء ثنائي الأبعاد سيطرة كاملة. هذا الجسيم على الفضاء ثنائي الأبعاد لديه خاصية أنه إذا سيطر سيطرة كاملة، يعني عدم التناظر في الفضاء ثنائي الأبعاد، عدم التناظر سيطر سيطرة كاملة، فإن الجسيمات التي تخرج من هذه التفاعل في الفضاء رباعي الأبعاد تكون غير متأثرة بالفضاء الخارجي. يعني مثلا النيوترينو غير متأثر بالفضاء الخارجي. ربما السبب، لا، أنا أريد أن أعكس الأمر عكسا، هو أن الجسيمات التي تخرج من التفاعل لديها كتلة عالية لكن مسافاتها قليلة، اللي هي حجمها قليل جدا. الكتلة العالية تأخذ في داخلها كسر التناظر كاملا، والمسافة الحجم الصغير يأخذ يعني يكون معدلات التدفق للفضاء يكون عاليا حوله. فهذه النوع من الكتل عالية لكن ليست بقدر أن يجعل الفضاء ثنائي الأبعاد يدافع عن نفسه، ولكن المساحة صغيرة أو الحجم صغير، حجم صغير جدا. هذا النوع من الجسيمات يكون غير متأثرا بالفضاء الخارجي، بشرط أن لا يجبر الفضاء ثنائي الأبعاد يفعل آلية الانتفاع النفسي داخله. فهذا ما يصل للنيوترينو. النيوترينو يستطيع أن يعبر الأرض دون أن يتأثر بها، الأرض كاملة دون أن يتأثر بها. وقد عزيت كثيرا من فيديوهاتي وكتبي بسبب أن هذا النيوترينو بالنسبة لأن معدلات التدفق الفضاء حوله عاليا، فإن هذه المعدلات التدفق عاليا تجعل النيوترينو غير متفاعل، وهذا واضح مثل تأثير المادة المظلمة، حيث أنه عند المعدلات تدفق عالية أو عندما كسر التناظر لأبعد حد، كسر التناظر في الفضاء ثنائي الأبعاد تجعل القوى الأساسية الثلاث غير متفاعلة، لأنه القوى الأساسية الثلاثة هذه تعبر عن كسر التناظر، لكن في النهاية تحتاج إلى كتلة متناسبة لها حتى تتأثر بها أو تؤثر عليها. فعند الأبعاد الصغيرة جدا فإن كسر التناظر هذا يجعل القوة المنشأة الناشئة من كسر التناظر غير ظاهرة. طيب، مرة أخرى، هناك قوة تنشأ من كسر التناظر في الفضاء ثنائي الأبعاد. هذه القوة تكون متناسبة مع الحجم الاريا التي حصل فيها الكسر. إذا كان اريا كبيرة شوية، يعني مثل الاريا التي تتحكم فيها الكواركات نحن نعلم كتلتها بالميجا إلكترون فولت. الإلكترون كتلته نص ميجا إلكترون فولت. إذا كتلة عالية ومساحة كبيرة، لأن الإلكترون مساحته ربما نقول 10 ناقص 19، أيضا ليس بالصغيرة، والكوارك 10 ناقص 18. في هذه المساحة وهذه نصف القطر وهذا الحجم تظهر فيه هذه الكتلة العالية. هذا الحجم هو ما يأخذ في داخله عدم التناظر هذا أو كسر التناظر هذا، بالتالي بما أنه حجم كبير شوية فإنه يجعله يتفاعل مع الجسيمات التي حوله كما تظهر في الستاندرد موديل وفيزياء جسيمات على الطاقة. النيوترينو يختلف. النيوترينو طاقته بسيطة جدا 10 أس -5، وهذا يعني أن حجمه صغير جدا جدا، لكن يحمل في داخله كثرة التناظر. بالمناسبة نسيت هذه المعلومة أيضا، كلما صغرت الأبعاد كلما قلت كثرة التناظر. لماذا؟ لأن حسب كتاب الحلقة 54 أن صغر الأبعاد يساهم في إرجاع التناظر. بالمناسبة هذه معلومة مهمة جدا جدا. صغر الأبعاد يساهم في إرجاع التناظر. كيف ذلك؟ بمعدلات تدفق المكان والزمان. كلما صغرت الأبعاد كلما زاد التايم دايليشن ونقصت معدلات تدفق الزمان والمكان. هذه معلومة في غاية الأهمية، وهذا يعطي تفسير لماذا النيوترينو لا يتفاعل. النيوترينو يحمل في داخله هذه الكتلة الصغيرة، ويحمل في داخله في داخل هذه الكتلة ليس كثرة التناظر إنما إرجاع للتناظر. يعني اذهبوا لكتاب الحلقة 54 أو تعال نذهب إلى الكتاب. هذا كتاب الحلقة 54 إلى الموضوع الذي ذكرته لكم. هذا هو اللي هو العنوان له أو الباب الشابتر له. هذا هو الشابتر. تفسير عدم التناظر داخل الكتل أو الانتراكشنز فيزيكال، يعني تفسير عدم التناظر داخل الكتل، أقصد طبعا كتلة البروتون والكتل الأخرى والانتراكشن. طيب إذا حصل أنه وجدت الكتلة، طبعا هذه تنطبق على الكتلة لكن يمكن أن نطبقها بدون الكتلة. هذه المعادلة تعال نقلب طبعا هذا الأمر مهم جدا، لهذا لابد لنا أن نناقشه بشيء من التفصيل. طيب هذه المعادلة تخبرنا ما يسمى بالبيزيس فيكتور أو متجهات الوحدة. بهذا الشكل يخبرنا عن متجهات الوحدة للفضاء الإنسان أو الملاحظ الموجود خارجا بدلالة متجهات الوحدة في للإنسان الموجود داخلا أو للملاحظ الموجود داخل. يعني كيف الملاحظ الموجود خارج يرى ما داخل الأبعاد الصغيرة اللي هو ECT التي تعتبر عن متجه الوحدة بالنسبة للفضاء للزمن، وهذه متجه الوحدة بالنسبة للمكان. أين هو؟ لا نريد هذا هو، هذا بالنسبة للزمان، متجه الوحدة بالنسبة للزمان، وهذا هو متجه الوحدة بالنسبة للمكان بالنسبة للملاحظ الخارجي. هنا عكسه تماما، متجه الوحدة للزمان للملاحظ الداخلي كيف يرى خارجا، وهذا متجه الوحدة للمكان للملاحظ الداخلي. طيب تعالوا هنا في متجه الوحدة لا أقصد هنا هنا ولا هنا أظن في متجه الوحدة نعم هنا في متجه الوحدة بالنسبة للنيوترينو كعنصر يتفاعل مع الفضاء الخارجي، نجد أن متجه الوحدة للزمان هذا يتناسب مع سي تكعيب على 4 R تربيع ناقص أسي أو في إي أسي ناقص نص اللوغاريتم الطبيعي 3 GM على سي تربيع R زائد 3 GM على سي تربيع R. هذا يعبر عن جرافيتي. بالمناسبة هذه المعادلة تعبر عن الجرافيتي مع قليل من التعديل، لكنها تعبر عن الجرافيتي، ليس فيها تعديل الحقيقة، تعبر عن الجرافيتي مباشرة. انظر إلى الدالة الأسية نجد أنها بالناقص. إذا عوضنا الكتلة M كابيتال بزيرو وآر أقصد بواحد وآر بواحد، هذه المعادلة تعطينا عدد صغير جدا جدا. وهذا يخبرنا بماذا؟ يخبرنا بأن متجه الوحدة بالنسبة للفضاء الداخلي يكون صغيرا وليس كبيرا. متجه الوحدة بالنسبة للفضاء الداخلي يكون صغيرا، بالرغم أنه R يمكن تعويض R كمان، يمكن تعويض R بحدود R نعوضه بحدود النيوترينو، يعني نقول أصغر من الإلكترون كثيرا، يعني نقول 10 أس ناقص 24 متر مثلا. فهنا R تربيع تعطينا عدد كبير لأنه مضروبة في C تربيع، C تكعيب، فتعطينا عدد كبير، لكن الدالة الأسية تعطينا عدد صغير، وهذا يعطينا معدل تدفق الزمان. فمعدل تدفق الزمان حول النيوترينو يكون صغيرا، مما يدل على أنه يحصل تايم دايليشن عند صغر الأبعاد. هنا أيضا معدل تدفق المكان، هنا أيضا معدل تدفق المكان أيضا يكون صغيرا. طبعا هنا أنا نسيت وأنا مفترض نعم هنا معدل التدفق المكاني يكون طبيعيا، لكن معدل تدفق الزمان يكون صغيرا. هذا معدل تدفق الزمان يكون صغيرا. هذا معدل تدفق الزمان هو ما يسمى بالتايم دايليشن. إذا عند صغر الأبعاد بالنسبة للنيوترينو يمكنكم تعويض هذه المعادلة. عند صغر الأبعاد بالنسبة للنيوترينو فإن نجد أن هناك تايم دايليشن عالي. الام لا تعوضها بواحد، عوضها بكتلة النيوترينو اللي هو 10 أس ناقص 5 كذا، هكذا أفضل. أنا عوضتها بواحد ستؤثر على المعادلة في الحد الثاني، بالرغم أنه تأثير على المعادلة في الحد الثاني لأنه الإشارة كلها موجب، وبالتالي لا يؤثر، إنما يزيد أيضا يقوي أيضا الفرضية التي ذهبت إليها. فإذا عوض ام ب10 أس ناقص 5 مثلا، أو عوضها بأي شيء، لأنه هذه الجزئية تمثل الفضاء الداخلي للنيوترينو. نحن لا نريد الفضاء الداخلي للنيوترينو، نحن نريد الفضاء الداخلي الخارجي للنيوترينو، وهي نعبر عنها باللوغاريتم الطبيعي لسرعة الضوء S6 على 16 جي تربيع ام تربيع. ام يمكن أن تعوضها بواحد أو تعوضها بكتلة النيوترينو الحقيقية، سنجد أن ام تزيد هذا الحد، والحد بإشارة السالب، بالتالي نجد أن هذا الحد سيكون كبيرا وسيغطي على الحد الأمامي اللي هو سي تكعيب على R تربيع، فهذا الحد يعطينا التايم دايليشن. إذا مع صغر الأبعاد يحصل تايم دايليشن. هذه خاصية أساسية في الفضاء، خاصية أساسية في الفضاء. طيب ماذا يحدث بعد ذلك؟ حصل تايم دايليشن. ما يحصل هو أن عند صغر الأبعاد فإن النيوترينو هذا يجعل النيوترينو لا يتفاعل، لأنه يرجع التناظر، وفي الفضاء الصغير، في الفضاء الصغير يرجع التناظر، وبالتالي بما أنه رجع التناظر فهذا يعني أنه لا تتولد قوة من أجل أن تعبر عن كثرة هذا التناظر وتجعل الجسيمات تتفاعل. هو طبعا التناظر لا يرجع إلى آخره، لأن الفضاء ثنائي الأبعاد سيفعل آليته، لكنه سيرجع إلى قدر ما، لأنه إذا رجع إلى النهاية فهذا يعني أن الفضاء ثنائي الأبعاد سيفعل آلية الانتفاع النفسي، لأنه تعتبر كتلة عالية. وهذا ما يخبرنا لماذا بداية الكون حصل التضخم السي، لأنه لدينا مسافة صغيرة، هذه المسافة الصغيرة هناك تناظر مرجوع في المسافة الصغيرة. مع ذلك مع هذا ربنا سبحانه وتعالى نفخ فيه بطاقة عالية وأودع وخلق الفضاء صناعي الأبعاد من قبل أنه يستطيع أن يدافع عن نفسه. فهذه الطاقة العالية في هذه المسافة الصغيرة، هذا التناظر المرجوع وهذه الطاقة العالية الفضاء صناعي الأبعاد دافع عن نفسه بقوة بتضخم دالوسية. طيب إذن هنا في هذه المعادلة، طبعا هذه المعادلة تعتبر تصحيحا لكتاب الحلقة 36 أو ليس تصحيحا كاملا، إنما معادلة مغايرة لكتاب الحلقة 36 و37 طبعا. طيب فنجد هنا عند الأبعاد الصغيرة الفضاء صناعي الأبعاد، الفضاء رباعي الأبعاد أو الفضاء عموما يحاول أن يرجع التناظر بذات نفسه، وهذا ما يدخلنا طبعا في الكوانتم لوب جرافيتي. يمكن أن من هذه المعادلات يمكن أن نناقش الكوانتم لوب جرافيتي بكل أريحية، ويجعل الفضاء يتقوقع على نفسه عند حدود 10⁻²²، ليس عند حدود بلانك. عند حدود بلانك حصل التضخم الأسي بسبب أن الأبعاد أصغر، حيث أن أبعاد حدود بلانك هي 10⁻35، لكن اللوب كوانتم جرافيتي تحصل في عند 10⁻²²، يعني أكبر من أبعاد بلانك. فإن الفضاء يتقوقع على نفسه ويحصل يعني مثل جرانولز، ويكون عبارة عن كمات متقوقعة على نفسها ويظهر لها كتل. طيب نرجع أخرى للنيوترينو اللي هو 10⁻²² متر، 10 قريب من 10⁻²² طبعا. في 10⁻² يحصل أنه للنيوترينو يكون من الفضاء ذات نفسه يحاول أن يرجع التناظر، وبالتالي القوة التي تنشأ بسبب كسر التناظر تكون قليلة جدا، مما يجعل النيوترينو هو inert أو خامل في التفاعلات المادية. طبعا هو يخرج من التفاعلات ال EW. لماذا؟ لأن ال EW عند أبعاد صغيرة 10⁻18، وهنا عند هذه الأبعاد تكسر التناظر بين الكتل، تظهر كتل عالية وكتل منخفضة جدا جدا. فكتل منخفضة جدا جدا من بينها النيوترينو، فالنيوترينو يظهر بطريقة طبيعية للإلكترويك. لكن النيوترينو فور خروجه لا يتفاعل مع الجسيمات إلا في ندرة عالية، بالتالي يستطيع أن يخرج من قلب الشمس إلى أن يصل إلى الأرض ويفوق الضوء في هذا. أيضا يستطيع أن يخرج من السوبر نوفا. طبعا السوبر نوفا هو انكماش للنجم، هذا الانكماش يؤدي إلى زيادة الجرافيتي في الأبعاد الصغيرة اللي في الإلكترويك ريجون. فهذه زيادة الجرافيتي أو زيادة الكتلة في هذا الريجون الصغير يفعل بطريقة أكبر كسر التناظر بين الكتل، مما يجعل كتلة عالية وكتلة صغيرة. من ضمن الكتلة الصغيرة التي تخرج هي النيوترينو. هذا النيوترينو عند أبعاده الصغيرة نجد أن معدلات تدفق الفضاء والزمان تكون قليلة، بحيث أنه يحصل تايم دايليشن. السبيس ليس بالكثير، لكن التايم يكون كبيرا جدا. تايم دايليشن، هذا التايم دايليشن يرجع التناظر، هذا يرجع التناظر يقمع على القوة المسببة للماتر انتراكشن، اللي هو القوى الأساسية الثلاث، الضعيفة والقوية والكهرومغناطيسية، وبما في ذلك الجاذبية أيضا. فهذا ما يجعل النيوترينو غير فعال. جميل، تعال نرجع مرة أخرى لمحاضرتنا. طيب أنا شايف المساحة اتملت، سأواصل الفيديو بعد ما أمسح أشياء. جميل، تعالوا نواصل بقية هذا الفيديو.
I hope I didn't forget anything important. We have encountered them along the way while we discussed the standard model at tree level, and that is why this is one reason why I was quite explicit and extensive in our tree level discussion, because all those things here are noteworthy. They of course can get lost if you only look at the detail, the technical stuff and write down Feynman rules and so on, then you do not see this, but there is a lot of very interesting physics hidden in the technical details, and which in particular becomes prominent if you compare the standard model with its alternatives. And so looking at this and to the fact that the standard model agrees so well with experiment is indeed quite laudable, that the standard model performs maybe better than its inventors could have ever dreamed. Okay, so I think we are good. Question. Yeah, so if we would include this into the Lagrangian from the beginning, then it would correspond to a non-renormalizable theory. Therefore, we do not include it. But there is this idea of so-called effective field theories, where you study extensions of the standard model by incorporating more and more higher dimensional operators, which one thinks could be generated by some other dynamical mechanism which we don't know. For example, new physics at very high scale, supersymmetry, 2 Higgs doublets. If the supersymmetric particles or the new Higgses are very heavy, then we do not see them in experiments, but they could have some effect. And one can typically take into account the effects of heavy particles by adding new operators to the standard model Lagrangian. In fact, one can prove that this is the most general thing that those heavy particles can do if we are only restricted to low energy observables. And therefore, extending the standard model by all possible gauge invariant operators of higher dimensionality would be a very model independent approach to studying what kind of physics could be out there, even if we do not know from which particles and which interactions it can come. And then these new operators are sorted according to their mass dimension. The dimension 5 operator behaves like 1 over mass. Dimension 6 behaves like 1 over mass square, and so on. So therefore, you might expect on very general grounds that the first effect of any new interaction that you would see beyond the standard model is an effect from dimension 5 operators. And there is just one single dimension 5 operator which is gauge invariant, and that is the one given neutrino masses. And so it is very natural to think that actually some unknown, but nevertheless some non-vanishing interactions from heavy particles do not see them in experiments, but they could have some effect. And one can typically take into account the effects of heavy particles by adding new operators to the standard model Lagrangian. In fact, one can prove that this is the most general thing that those heavy particles can do if we are only restricted to low energy observables. And therefore, extending the standard model by all possible gauge invariant operators of higher dimensionality would be a very model independent approach to studying what kind of physics could be out there, even if we do not know from which particles and which interactions it can come. And then these new operators are sorted according to their mass dimension. The dimension 5 operator behaves like 1 over mass. Dimension 6 behaves like 1 over mass square, and so on. So therefore, you might expect on very general grounds that the first effect of any new interaction that you would see beyond the standard model is an effect from dimension 5 operators. And there is just one single dimension 5 operator which is gauge invariant, and that is the one giving neutrino masses. And so it is very natural to think that actually some unknown, but nevertheless some non-vanishing interactions from heavy particles are responsible for generating the neutrino masses, and then you would kind of quite naturally understand why the neutrino masses are very small, because they involve this 1 mass suppression, and also why you do not see any other deviations from the standard model, because all other deviations would be suppressed by an additional power of a heavy mass. So the effects would be much smaller than the small neutrino masses. So that is a very natural and motivated way to think about this. However, it doesn't guarantee that it's the right way to think about it. This would give rise to Majorana neutrino masses, but we don't know. The neutrino masses could also be Dirac masses. And therefore it's important to figure out what is the nature of neutrino masses in order to know how to extend the standard model in this context, for example. Other questions? Yes. Then let us stop here. In the afternoon we have exercise, and next week I will summarize the Feynman rules, and then we do calculations and renormalization. Okay.